the red light? Okay, good. Alright, well, good morning everybody. The last couple of lectures we have been... By the way, the tie is not for the video. I know you're thinking the tie is for the video. It's not. This is our meeting today, so I'm going to run from a meeting to do this lecture and I have to run back. So it's multitasking. Alright, so the last couple of lectures we've been looking at Root Locus. And we've been looking at how you construct it. So let's just kind of review again the basic steps in constructing a Root Locus. So when you're given a transfer function, let's say you're given a closed loop system, then when you're given that closed loop system, a closed loop feedback system, what's your first step if you want to go about plotting the Root Locus for that system? Taking what? Sorry? Nothing? What's the first step? It's not really easy. Transfer function. What kind of transfer function are we looking for? Open loop transfer function. So how do we get that? KGH basically, yeah. So it's KGH. So you break the loop at a point, and then you take each element, multiply them together. So you get your open loop transfer function. First step. What's next? Poles and zeros. That's the next step. So then once you've got your open loop transfer function, you can find your open loop poles and zeros. What do your open loop poles and zeros represent? What do they represent? Your roots and your something else? Yeah? Anyone want to elaborate on that? So I'm on the right track. What do those open loop poles and zeros represent? Just think of it in terms of the transfer function. The poles, what do they do to the transfer function? Send it to infinity. So whenever you get a pole, your transfer function goes to infinity. So that represents the point in your system in which generally your gain k equals 0. It's a point of departure of the movement of your roots. And remember, a root locus is basically the way in which your roots move as you change what? As you change gain, or anything else actually. It could be any parameter in your transfer function. So it could be just tracing the movement of your closed loop roots. So you use your open loop poles and zeros, but then you look at the closed loop roots, the movement of the closed loop roots, as they move from where to where? From poles to zeros. And so if you have a transfer function that has 3 poles and only 1 zero, you've got one of those poles will end up in a 0. What happens to the other 2? They have to go off to infinity at some angle, yeah? And so if they're going off to infinity at some angle, how do we determine what angle? So we use our formula. Alright, which formula is it? Brackets 1 plus 2k pi over n minus m. Okay, how many values of k do we have? How many values of k would we normally use? Well, 3 if you've got what? 3 poles. So it's usually 1 value of k per pole. Because generally speaking, well, it's 1 value of k for each pole minus 0, for each n minus m. Because that's how many, what we call asymptotes, go off into infinity. So we want one angle for each asymptote. If you've got 3 poles and 1 0, then in that case you'll have 2 asymptotes, because 1 pole will go to a 0, but the other 2 will go off somewhere else. So we'll have to have k equals 0 and k equals 1, or 2 values of k. Okay, so we're just kind of getting this stuff going back in our minds. So we've got the angles now at which the asymptotes diverge and go off to infinity. So what's the next step? What else do we have to do with the asymptotes? In order to be able to plot our asymptotes. Sorry? find the crossing points on the imaginary axis. You've got to head one step then. But you have to find where if you're plotting asymptotes as well as the angle, you need to find the point of their origin on the real axis. Okay, so that's the departure, this is what we call the centre of the asymptotes, or sigma c. Alright, so we have to find sigma c, and we can plot our asymptotes. What else can we do before we even get to the point at which the root locus crosses the imaginary axis? There's something else we can do first. Well, we might need to find the break-off points, that's right. But even before that, we can plot a part of the locus right away. Which part can we plot before we have to get into how it moves away from the real axis? You recall we can actually plot the root locus on the real axis? Yeah? And what was the shortcut I taught you how to do that? So where you stand, if you look in the positive direction on the real axis, if there's an odd number of poles or zeros on the real axis, you're on a locus. If there's an even number, you're off a locus. So you can basically track across from the positive side of your real axis, to start this side so it's oriented correctly for you. So if you're tracking across a pole, pick up a locus. Cross another pole, drop the locus. Cross a zero, pick up a locus, etc. Okay, so it's pretty easy to put that to see where the locus lies on the real axis. So then we get to determining our breakaway point. How do we determine our breakout point for where the locus leaves the real axis? That's the point at which dk by ds equals 0. In other words, the change in your gain, or the angle of the relationship between your gain and your s value equals 0. Okay, so it's like a maximum point in an equation. And so we can use that. How do we use it? We've got that criteria, dk by ds equals 0. How do we use it? To be able to get an actual value of s, where we get our breakout point. Sorry? The auxiliary equation, right, so we use our auxiliary equation, and when we get our auxiliary equation, which comes from which other tool? Around those, we can get our auxiliary equation, or our characteristic equation actually. Beg pardon, it's the characteristic equation for this one. So you have to use the characteristic equation, and that should be, if you've got a transfer function that has a value of k, and we're looking at the change of the position of the roots with k, then our characteristic equation will have a k in it. It will be s in terms of k. So then we can differentiate the equation, get an expression for dk by ds, set it to 0, and solve the resulting polynomial. And hopefully, it's a quadratic, easy to solve. It might be a higher order polynomial, which is a bit more tricky to solve. So generally, for the purposes of doing these things by hand, I try to make sure your polynomial is a quadratic when you differentiate your characteristic equation. Okay, so you're still with me, tracking what we're doing, how we're putting this thing together. So now we've got our breakout points, and we know our locus go off from the real axis from that point. Now, before we move on, what does that point of departure represent? Where the roots diverge from the real axis, what does that represent? It means something. It's a certain value of k. Remember, k will start at 0 at your poles. As k increases, you'll be moving along. If we have poles on the real axis, we'll move along the real axis to a certain point at which those poles will start to, the closed loop roots will start to diverge from the real axis. There will be a value of k that will cause that to occur. What does that value of k represent? It's where you start to get some damping, that's right. So you start to move towards a system that hasn't just got, that's got some what in the response. When you get damping, what does that correspond to? When you move away from the real axis, you start to get an imaginary part in the roots. And when you get an imaginary part, what do you get? Oscillation. So the point of divergence of your root from your real axis corresponds to the introduction of some oscillation in the response. In other words, as your value, we looked at this last time, when we looked at MATLAB, and we changed our, as we literally moved our position of the roots along the real axis. As soon as you start to get or break off the real axis, you start to see a little bit of oscillation. And that represents the point at which the damping ratio goes above 1, or below 1 rather. So it goes from 1 to 0.9 or something. And then as you move further and further away from the real axis, or as you move closer to the imaginary axis, then what happens to your damping ratio? Heads towards, well, let me ask it this way. If you have a locus which, let me draw it up. I think we've gone far as we can. So we have our nice conventional 3-pole, no zero type root locus. So we know we can plot the position on the real axis. This is real. This is imaginary. And we're talking S-plane here. This is our S-plane. So we know that we've got our point of divergence and breakout point, say here. And our locus is going to go off, because we've got 3 poles and no zeros. Our asymptote angles are going to be what? 60, minus 60, and 180. Well, no 180 because that one already goes off. So we're going to have a centre of asymptote, say it's here. We're going to have our asymptotes plus or minus 60, so that defines our asymptotic direction of the locus. And then we know our locus will break off and head eventually towards convergence of the asymptote. Right now, the question I'm asking is, we said at this point, this corresponds to our damping ratio equals what? 1. Okay? So anywhere, if you've got your closed loop roots moving along this locus, anywhere until the point where it reaches the breakout point, then this region here, zeta, is greater than 1. Okay? So in other words, it's what kind of damping? Overdamped. So your response, when you get this kind of overdamped situation, so to plot the response, it's going to be, this is your objective, sluggish. When you get to the point where zeta equals 1, the response will certainly not be overshooting at all, but it should pretty much match your set point. Okay? But it's still sluggish, relatively speaking. So if you want a system that has a much more rapid response, you're going to have to push it. You're going to have to probably have complex roots. So now we're pushing our value of, what's causing this root to move again? Increasing something. Let's say we're increasing our gain. So as we're moving in this direction, that means our gain is going up. So increasing K coming along here. So we're pushing our gain up to a point where our roots diverge from the real axis. And we said already, that means we're introducing oscillation. As we continue to increase our value of K, what's happening then to our value of zeta? What's it going to approach? 0. Sorry. So zeta's approaching 0. Then when it hits this point here, what happens to zeta? Right? Zeta equals 0 here, that's right. Okay, so we can see the relationship between the value of our damping ratio and the position of our roots. And remember, we have the standard second order responses. And we had a set of responses that look something like this. This is our final value. We had a series of curves. Looking kind of like this, and the data is in your notes. And it's in past papers, and you get it in your exam paper at the back as well. So this set of curves has a little indicator on it saying zeta going towards 0. So each one of these have a set of values zeta. Zeta equals 0.1, zeta equals 0.2, etc. And this one down here is zeta equals 1. And we know that where it does this, it crosses over, what happens to the system? What's the condition of the system where it crosses this imaginary axis? Simple harmonic motion equals marginally stable. Okay, good. So we got our movement towards a point which is marginal stability. Now going back to the issue that we were discussing before, how do you find the point at which this crosses, or the value? The real value is 0 when we're back, but we need to get the imaginary value. So we can actually put a point on the axis where this crossing point will occur. How do we get that? That comes from auxiliary. So this is the right. We get this by. Get this point from our round filaments, yeah? No? Yes, round filaments. And then brackets, auxiliary equation. Alright, so that's basically where we're at. I think we basically got to that point, didn't we, last time? So it's important you know how to construct a root locus, and because that's always something you're going to get in exams. Apart from that, it's a basic platform for understanding the dynamics of your control systems. So it's not only because you get it in exams, you get it in exams because it's a kind of fundamental part of understanding the system. So let's move on with the lecture, which is, I think this is the third session on the same lecture, but we'll keep moving on with this one. So what I want to look at now is this issue of dominant poles. We know that the transient response to the system can be equated to a sum of exponential terms. Right? So if we were to take our position of our roots, then if we find the roots of the equation, the characteristic equation, they tell us about the nature of the response of the system. And the nature of the response is defined by these exponential terms. We know that because if we take inverse Laplace transforms, when we've done our partial fractions approach, take inverse Laplace transforms, we get a series of usually some kind of constant and a series of exponentials. Alright? And those exponentials are decaying. If it's a stable system, they decay. So the exponentials basically just tell you a transient response. It's a time-based thing. Eventually it will have no effect on the ultimate state of the system. But over a period of time it will have some effect. So the contribution of each term is determined by one of the roots of the characteristic equation. So if we've got 3 poles, we've got 3 roots. And as you increase in k, well, we know this one moves from here towards the breakout point and this way. This one will move from here towards the breakout point and down. And this one will move from here outwards. We didn't plot them on this locus here. Alright, so we've got these 3 roots moving away from our poles. And each one of these roots corresponds to one term of the characteristic equation, one of the roots of the characteristic equation. And what you find is each root doesn't contribute equally. Right, so the reason for that is that some roots will dominate the response because some roots will decay a lot more quickly than others. So they might have some impact in the very first period of the response, the time response, but it's going to decay so quickly that it doesn't really have any long-term effect. Other roots are going to hang around a lot longer, and so they're going to be more dominant. So we've got this issue of dominant roots. So if we look at this example, we've got gain k over s plus 8, s plus 4, s squared plus 3s plus 20. Alright, so what are the roots of this transfer function? And what's the response going to look like? Well, Well, let's just do it in general terms. We can know that you're going to have some constant A, so we don't have to do all the partial fractions and so on. I mean, anyway, it's expressed in terms of K, so we can't get eventual value. So let's just use general constants. A, e to the minus 80, we get that from this term here, plus b, e to the minus 40, we get that one from here. And then this one's complex. You get the roots of this quadratic, they're complex. And so we can express complex numbers in different ways. We can either express it as real or e to the real plus imaginary part. We know that imaginary part is representing an oscillating aspect. So hopefully from your maths you recall that you can express a complex number like this as a sinusoidal term. So if we express this part in sinusoidal terms, then you get some constant c, e to the minus 1.5t, so this will represent the real part. That's decaying, but then as it decays you've got some oscillation on that term. And that oscillation has a frequency of 4.2t and the phase shift phi. Okay, so we've now expressed the roots of this in the terms of our transient response. We don't know, there's probably be some constant term which should be the final value, but we're not looking at that, we're just looking at the transient terms in this case. So these constants here are determined by the initial conditions which we don't know. We're just looking at the form of the equation. So if we were to plot our polar locations corresponding to that characteristic equation, then our polar locations will be at minus 8 from this one, from this minus 4, and then minus 1.5 plus or minus 4.2. Okay, so we can plot our polar locations on our root locus for this characteristic equation. Now you can see, if we take the transient response, you've got these three elements that are decaying. This one is the minus 80, decays very quickly. This one, the minus 40, decays more slowly. And then this one here, the red one, this is the oscillatory term. This decays within an envelope defined by minus 1.5, and it's got a 4.2 oscillatory component. Okay, so it's going to continue to oscillate at 4.2 J. So that defines the rate of oscillation that you get for this particular system. Okay, so basically this minus 80 is not going to have much effect on the transient response because it will disappear quickly. Minus 40 will have some effect, but the dominant effect in this case is this oscillatory term. It lasts longest, and so it's going to be dominant. So which poles correspond to this term? It's these poles here. See that my animation? So these ones that are flashing with circles around them, these are the poles that produce this red line, produce this dominant response. So we can say the total response is dominated by the decaying sinusoidal roots of this term are much closer to the imaginary axis. That's the key issue there. It's the location of the roots in relation to this imaginary axis that's important. Right, so what we can say is if you've got roots that are closer to the imaginary axis in comparison to the other roots in the system, even though this system, what's the order of this system? It's a fourth order system. We don't have standard responses for a fourth order system, right? We only have standard responses for a second, and actually we have them for a third order system as well. But we don't really have standard responses for a fourth order system. But according to this, because we have dominant poles that are closest to the imaginary axis, and those dominant poles are second order poles, then you can approximate the system to a second order system. Okay, so that's why it's useful. Because if we can say, okay, well, our dominant roots, let's say in the response, are second order, then we can assume that the second order characteristics apply to this fourth order system. So we can still predict what the transient response will look like on that basis. So since dominating roots are second order, the system may be approximated by an equivalent second order system. Make sense? means that they can use all those nice documentation, all that, those nice standard responses and so on, to describe the response of our system. And it also means that our performance is described in terms of our standard second order or prototype second order system, what it's called. Okay, so our prototype second order system is where it says omega n squared over, what is it again? Omega n squared over s squared plus 2 zeta omega n s plus omega n squared. Remember we looked at that prototype second order system? So the system is described in terms of key characteristics which are damping ratio and natural frequency. Let me write stuff here. So we can say G of S equals omega n squared over s squared plus 2 zeta omega n s plus omega n squared. This is called prototype second order system. Why prototype? Well, prototype is just saying it's a standardized form, basically. It's a standardized form. So here we have a response that's described in terms of two variables, omega n, or two features of our system, our natural frequency and our damping ratio. So we've got this effect that the higher order system has been reduced to a second order approximation, so we can use that second order system data. Okay, so is that all making sense? Clear as? I think when you go over it and you start using it in practical examples, it makes sense. But what I want to make sure that you will do is grasp the meaning of the root locus, not just to be able to answer questions on it. Right? And some of the questions I might give in the exam would ask you to interpret it or to indicate the meaning of it. Right? Because it's a very useful tool. Like I think when we were talking about it at the start, we said it's like a tool for visualizing the behavior and the dynamics of the system. Right? And so if you can sketch up a root locus for a system quickly, then that will give you a sense of what the system is going to, how it's going to behave, how it's going to change as you change certain parameters in your control system. Now, moving on a little bit then, so let's look at this equivalent second order system. This is our GS, which I just wrote up on the board in the same form. The poles of this transfer function, if we were to ask you what the poles are, and you need to use your quadratic rule, so you could just say the poles are minus b plus or minus root b squared over 2as, root b squared minus 4ac over 2a. Right, that's our quadratic rule. So if we plug these coefficients into that rule, then this will be the solution we get for s. And so note that it's potentially or likely to be a complex number. We've got a j here. So we've got a real part, which is minus zeta omega n, and an imaginary part, which is omega n root 1 minus zeta squared. So if this is the poles for our prototype second order system, then how do we plot those? This is our real imaginary. What's going to be the location of these poles? So we've got a value here of minus zeta omega n, and j is going to be omega n root 1 minus zeta squared. And there'll be a complex conjugate down here, minus omega n minus zeta squared. Okay? So, if we were to draw a straight line this is going to be. What's the value of that? Quickly work it out. Sorry? What's the value of this line from the origin to your pole? If you know the location, the real position, and the imaginary position of this pole, what's the length of this line? Quickly, you can jot it down and look it up. First one to do it gets a star stream sticker. Which I'll bring next time.
Yes, stuff. Yes, I don't know what it is. I have one already.
Sorry?
What do you want?
It's what? Oh, omega n? Alright, good. Correct answer. John King, star student of the day. Congratulations, John King. It's John. Whatever his name is. King. I know it's King.
Frederick.
That's the name of my great-great-grandfather. Alright, so you see the family connection. Alright, so we found that the value of omega n is given by the distance between the origin and the close and this pole here. Now we can use that. If we were to plot a root locus, so we had some kind of locus. Let's do our 3 poles again. This is a simple example. So if we have a locus like this one here, we want to identify the location of the closed loop root. So we've got a root here that we're interested in, let's say it's here. Call this R1. And if we want to know what's the natural frequency for that particular root there, if we just measure the length of this line, it gives us omega n. Alright? Now if I was to ask you the next thing, what's this angle here? Theta. Can you calculate theta for me? Yeah.
The length of the red line is omega n.
Right, well for this particular system, so for this system which is giving us the green locus, then if you've got a closed loop root at position R1, then the length of this line is going to give you the value of the natural frequency omega n for this system at this particular point. Right? This particular value for its parameters. And it's also going to have an associated damping ratio at this point. So what I asked them is, okay, let me rub off some of the things here. Let's come back then to the original black line. We already calculated the length of the hypotenuse, which gives us omega n. What's the value of theta? Now let's use, well, what we know, we can use either actually, but let's use cos, let's use the cos. So cos theta equals theta minus theta omega n upon omega n root 1 minus theta. Hypotenuse, sorry, yeah. I was getting concerned then, it wasn't quite right. So these cancel, equals minus theta. But then because of the properties of cos minus theta equals cos theta. Okay, because it reflects about 180 degrees, isn't it? Or 90 degrees, which is the cos. So cos theta gives us our value of theta. So if we have plotted a root locus, and we've identified the point on our root locus, R, then for that point we can identify both our value of natural frequency, which is the length of this line, and gamma here, we can find cos gamma equals our damping ratio is zeta. Okay, so we can get a value of both our natural frequency and our damping ratio for a specific point on the root locus. So we'll go through that and describe it kind of on the board. We'll go through it in the notes now. So one pole of the complex conjugate pair is located at P1, as shown in this diagram. So this is P here. We're located at P comma, rather, shown in this diagram. So here's P, a distance omega n, and omega n root 1 minus theta squared. We call this omega d, which is our damped natural frequency. So our damped natural frequency is the imaginary value of the location of P. And then, as we just did, we can calculate the length of this line as omega n, and the value of this angle, cos of that angle equals our damping ratio zeta. Alright, so I think we've done all this already. Kind of been through this whole segment, what we just did on the board. But it's there in the notes. So in the figure, cos of gamma defines what's called a damping line. And the distance of point P from the origin is equal to the natural frequency of the system. Now we can actually, remember you might have various different values of damping. As you change your value k, and you move your pole, this root R, up and down your locus, every different point on that locus is going to have a different damping ratio. And what we sometimes do is draw a series of damping lines at different angles. Each damping line will correspond to a particular damping ratio, like you might draw one that's 0.1, 0.2, etc., etc. So then you can see again, it's a visualization so you can see exactly where each damping ratio or each type of response is going to come on your plot. Alright, so next step, we want to actually, say we've got a system, we've plotted the root locus, and for that particular root locus we want to say, you might have in your specification for the system, this system needs to have a damping ratio of 0.6. And it needs to have a damping ratio of 0.6 because that gives you the kind of response we're looking for from the system. So if you say, okay, give me a system with a damping ratio, give me the value of my controller gain k, that's going to give me a damping ratio of 0.6. How do we do it? And we've got everything we need, or we've got all the tools that we need right here actually. Okay, but the key element is we need to be able to work back from a particular location on this locus to what value of gain k is going to put me on that location. And if you recall the one thing that we did last time, then when I moved the locus, or moved the root along the locus, then we saw how the value of k changed. So I'll just open that up and come back. Look at that. Alright, so if we take the value, a characteristic equation, we know our characteristic equation is that. We can rearrange it, and that will give, in order to give ourselves an expression for k. In this case, k equals 1 minus gh, 1 upon gh, minus 1 upon ghfs. So the modulus of k is minus 1 upon, or the modulus of minus 1 upon ghfs. So we can use that identity if we have an open loop transfer function that has this kind of form, which is like our standard form, expressed in terms of poles and zeros. Then, if this is true, what's the minus 1 upon gh of this? Is basically inverting it. And if it's minus, if it's modulus, the minus doesn't really matter. So it gives the value of k, which is basically the modulus of all our s plus p1, s plus p2 into s plus p3 over s plus z1, z2, z3, etc. So if the location of a closed loop pole is known, like R here, we know the location based on a defined damping ratio, then k can be determined graphically. You can actually measure it off. Because the modulus, this modulus here is really the distance between the pole and of pole P1 and the point on our root locus, in that case R. Okay, so if we take all the distances from our poles to our point Q, which in this case is the same as my R here. This is the closed loop pole. And the distance to the 0, then we can actually calculate the value of k that gives us that point Q on that closed loop pole Q. But the important thing is here, the real and imaginary axis of the root locus diagram must be drawn to the same scale. Right? And that's a common mistake when we're doing root locus by hand. People will do like, find that the scales aren't working, so they'll do like 2 or 1 centimeter per gradation along the real axis, but they'll do like 4 centimeters per gradation, or 4 centimeters per gradation along the imaginary axis or something. So you end up with uneven scales in your real and imaginary axes. And that messes you up, because when you go to measure distances, the distance, say QZ, you can't measure it off directly. Basically, you'd have to measure Q to Z and Z, and then, or you have to measure the horizontal and vertical distances, and then use Python to get the length. So once you plot the same scale on your real and imaginary axis, you're good to go. You can just measure using a ruler. You do a manual plot, measure directly QZ, QP1, QP2, QP3, etc. And then value of k is the distances of the p's, the poles, distances from the closed loop root to the poles multiplied together, divided by the distance to 0. Now, if you don't have a 0, right, effectively, you just use a 1 for the denominator here. Okay, so that 0 effectively saying the 0 is going off to infinity. If you don't put 0 on the bottom and get the k, it is infinite. Okay, so if you don't have a 0 in this particular transfer function, just use 1 for the distance on the bottom. Okay, just multiply the distance to all the poles. The other thing that can happen is that you sometimes get a value or a transfer function like this. Let's say a closed loop system looks like this. Where you control the k, and then you've got a transfer function that might have 50 over s squared plus 3 plus 2. Okay, so if we have a transfer function looking like this, your true value of gain k is what? You take your loop transfer function and say over gs equals what? What is it? Loop transfer function. 15k over r s squared. Okay? So the true value of k in this case isn't k, it's 15k. Right, so that means when you find the value of k here, what you're really finding the value of is 15k. So if you multiply all these up, then it comes to 100. The value of k is 100, the value of 15k is 100. And that means if you want to get the value of k, you have to divide 100 by 15. Just the full numbers. Okay, so you have to bear that in mind as well. Check what the k actually looks like. Okay, so here's an example. I think you could probably try this in your notebook, or paper, or scrap, or envelope, whatever you have. Okay, so I think you could probably just try it, see if you can sketch it, and then we'll use that root locus to identify the value of k to give us a given damping ratio. Incidentally, we're looking for a damping ratio of 0.5 on the system. Okay, so if you get that far, you can see if you can find the value of k